The ImPACT Tough Robotics Challenge program aims to raise the robustness of technologies so that robots can work in extreme environments such as sites affected by disasters. Our goal is to achieve the ability to gain access to places hard to reach, to see, hear, and touch, even under poor conditions, to retry despite failures, and to establish compatibility with the disaster environment in order to accomplish tasks. In order to create tough technologies, we are developing robots along with field evaluations under simulated disaster conditions. By creating a collapsed house simulating the Kumamoto earthquake and a mock-up of industrial plants and infrastructure where the disaster prevention paradigm is vital, tests are conducted repeatedly under rigorous conditions. Ultimately, we aim not only to instigate technical disruptive innovation, but also achieve social disruptive innovation that offers disaster prevention solutions, as well as industrial disruptive innovation that helps create new businesses. Cyber rescue canines aim to dramatically improve a rescue dog's ability to find people in rubble piles. We are developing cyber-enhanced suits with IT functions for dogs. The dog's behavior is being monitored on the map using a GPS and an IMU integrated in its cyber-enhanced suit. Articles left on the scene provide important clues for rescue search, but it is difficult for a dog to discover those items by itself. As video images transmitted from the cyber-enhanced suit are not quite up to the quality required, it takes a long time for a human to find the personal effects of the victims. It appears that image recognition has spotted a blue shoe automatically. On the computer display, the shoe is marked in orange. As shown here, the application of a machine learning technique, a type of artificial intelligence, enables automatic discovery of items registered beforehand among numerous images transmitted from cyber rescue canines. The dog has detected the scent of the victim. Search is extended to inside a sewer pipe. The victim is found in the pipe. Thanks to the image recognition function, the orange helmet worn by the victim is identified automatically. The search capabilities of rescue canines have thus dramatically improved. A thin serpentine robot called Active Scope Camera is capable of looking for survivors in the debris of collapsed houses. The robot is designed to worm into narrow spaces in the rubble, find victims quickly, and investigate surrounding conditions. A flexible 10-meter cable, equipped with ciliary vibration drive mechanism actuators, can crawl its way through small gaps using a distributed drive principle, reaching deep into piles of rubble. In order to remotely control robots in the rubble pile, the abilities to see, hear, and touch are essential so that we can exactly recognize the surrounding conditions during the search. Through multiple vibration sensors mounted at the tip, the robot estimates the direction in which the active scope camera has come into contact with something. The display indicates it in red in the camera image frame, and vibration gives intuitive feedback to the operator. The robot automatically discovers a pink hat left in the pile of rubble using image recognition. As the active scope camera continues its way deeper into the rubble, using multiple speakers and microphones inside the robot, it is possible to estimate the robot's shape and posture by measuring the transmission time of the sound. We are thus able to learn the location of the robot in the rubble. By processing sounds caught by multiple microphones, voices muffled by noises can be filtered.
ここにいます。助けてください。
This is how robots can find a victim trapped in a collapsed house and investigate the situation. In the Aerial Robot Project, we are developing technologies to ensure disaster prevention under adverse conditions, such as confined space, strong wind, and rain. In the previous field evaluation meeting, we demonstrated that the mini surveyor could fly in strong wind, as well as in and out of structures. This time, we will conduct an autonomous flight in rain, using the robot's autonomous flight function after taking off from water in a tank. Flight altitudes are measured using a barometer designed with the ingenuity to ensure the accuracy of atmospheric pressure readings even in a sealed waterproof structure. The mini surveyor autonomously positions itself precisely over a water tank with a diameter of 2 meters and successfully lands on the water. Takeoff and landing at sea or on a river are crucial for marine rescue operations. Multiple microphones on the mini surveyor help catch calls for assistance on the ground and find victims. Please take a look at the circle on the right-hand side of the screen. The direction of the person who has blown a whistle has been recognized automatically and indicated. Despite the loud noise of the propellers, the direction of the sound has been successfully identified. As shown here, we are developing technologies to enable search for victims and investigation of situations under severe weather conditions. In the Construction Robot Project, we are carrying out research in our aim to create next-generation construction machinery capable of coping with emergencies and carrying out recovery work in harsh environments at disaster sites. In order for robots to carry out complicated tasks or move, it is essential to be able to monitor objects and the surrounding conditions from multiple viewpoints. This robot is equipped with a drone capable of flying for long hours thanks to its wired power feeding system, and it shows bird's-eye view images on the cockpit display. Additionally, in case strong winds prevent the drone from flying, it is possible to create virtual images by combining images through a number of cameras on board the robot. The point of view can be changed freely. Reaction force received on the arm of the robot is fed back to the control stick, enabling the operator to feel the force. Contact with an object is measured by a vibration sensor, with an enhanced mode of the contact sent to the operator. For carrying out heavy work with high accuracy, we have successfully raised the response speeds and precision of the hydraulic system, which drives the robots to a new level compared to those of existing construction machinery. Such high-precision tasks were made easier thanks to this progress. During disasters, smoke or fog cannot be an excuse. This robot has an onboard far-infrared camera that enables it to do its job, looking at objects even in a smoke-filled environment. As shown here, we are aiming to develop next-generation technologies that enable the operator to fully understand the on-site situation and operate robots remotely with ease under disaster conditions. Legged robots are designed to perform dangerous jobs for humans, like industrial plant accident inspections. Warwick 1 is a four-legged robot that has achieved higher output and the storage of wires inside its body by adopting frameless motors. As well as normal walking and ladder climbing, it can crawl with its body hugging the ground, thereby achieving complicated movements on rubble piles. For the remote control of robots, It is essential to operate while checking the surroundings of the robot. For this purpose, a bird's eye view is effective in showing robot movements. However, onboard cameras do not provide an overhead view. So we have developed technologies to create virtual overhead images by superimposing the robot's movements with computer graphics on past images that the robot shot a few seconds ago. It is extremely difficult to move on rubble piles caused by explosions and collapse. For example, the Fukushima Daiichi nuclear power plant disaster. However, we are hoping that our studies in this area will provide a significant breakthrough. Thick serpentine robots are designed to move in narrow and tight places, such as pipes in industrial plants and infrastructure to conduct inspections. Wrapping around pipes, going over protuberances such as flanges, and moving in a so-called spiral twisting motion, they can conduct visual inspections. The robot is covered with pressure sensors so that the constriction force on pipes can be adjusted and the robot can be steadied to avoid sliding down even on vertical pipes. When moving inside pipes, it shifts by adjusting stretching pressure along the wall. With speakers and microphones installed at the entrance of the pipe and on the robot, the location of the robot inside the pipe can be estimated by measuring the transmission time of sound. It can even move on uneven surfaces with complicated shapes, twisting its body and negotiating obstacles. The aim of the thick serpentine robot is to conduct inspections in places in plants that are difficult to reach. As shown here, the goal of the ImPACT Tough Robotics Challenge is researching and developing tough robotic technologies that can perform emergency response, assist in recovery operations, and contribute to the prevention of disasters more effectively, safely, and quickly. For the safety and security of humanity. ImPACT.